Cell phone is an interesting platform that we scientists are realizing how powerful it is and what it can really enable more and more every day. We have more than 5 billion cell phone subscribers in the world. Right. And 70% of these cell phones are actually being used in developing parts of the world. 70%. So there's literally no landline, no infrastructure, but the cell phones are working in Africa, in different parts of the world, like South Asia, South America. And we are realizing that the embedded components within cell phones, in terms of hardware and software, in terms of optical components, are really fairly advanced to conduct advanced microanalysis for specifically diagnosis. And that's the theme of my research. We are creating new imaging modalities that can be integrated onto cell phones to look at cells, to look at bodily fluids for making diagnostic predictions. What we have in here is actually a microscope that is working based on computational imaging. Essentially, it is a microscope that doesn't use lenses. So the lens function itself is replaced by algorithms creating digital images of specimen at the micron scale, at a scale that is smaller than 1/1,000,000th of a meter, to look at morphology of cells. The enabler for this is, of course, computation, but the other enabler is the CMOS Imager. You're recording me through a CCD, but what we have, the equivalent of that on cell phones, is a CMOS Imager. It's a silicon chip that is maybe half a centimeter by half a centimeter, and that has so many small pixels that are sensitive to light. And that's how you kind of record images. The CMOS industry has done a fantastic job of making these cell phone cameras so advanced with so many megapixels, so small pixel sizes. That enables us to really use them as a fantastic computational microscope that can remove the function of a lens and bring in computation to make up for the lack of complexity. So in this device that you see here in my hand, there's a light source that is a light emitting diode, the same thing that we have at the back of our Blackberries. Whenever there is a new email, the thing that blinks is an LED. Yep. And you load your specimen from the side using a microscope slide or a microfluidic device, regular slide that you carry your sample. And this light emitting diode here shines. There's no lens in here, and it essentially scatters off the cells that you've inserted. Essentially, this is detecting shadows of specimen. Okay. There's no lens. Just like I bring my hand close to the table, if you bring the cells close to the CMOS imager, you will capture their shadows. What is different between my shadow and a cell's shadow is cells are semi-transparent because they're small. They're a couple of microns. So light can penetrate through and scatter from the three-dimensional body of the cell and cast a unique fingerprint-like shadow. It's textured. Then what we do is we take those shadows, process them, and digitally focus them back to where they are located. That digital focusing is the same thing that the lens does, except it's done through computation. This way you can actually create images that can look at large areas of, for instance, blood smear, and look at cell morphology at a resolution that is half a micron, 1/2,000,000th of a meter resolution scale, using computation. That's how this lens-free microscope works. Actually, it's based on digital holography. The shadows that I've described to you, physically, they're actually holograms. Even though you're not using a laser, they are still holograms because this gap here is spatially designed to give you a unique advantage to light. The light actually picks up some spatial coherence so that it becomes almost like a laser light as far as the cell is concerned. So this is actually a fluorescent microscope and a flow cytometer at the same time, where we can load specimen. There are some light emitting diodes there which actually excite the specimen that you inserted from the side, and then the fluorescent emission is imaged by the cell phone, and there is a tiny filter here which essentially rejects the excitation light. This geometry allows us to create a wide field fluorescent microscope that essentially is quite powerful for looking at large specimen volumes and large specimen areas.